I think it's working.
Yeah, it's just making a lot of noise.
What
It's
is
got to
it?
be a little higher up, and then we can turn the volume down on the.
No, I think I need the volume up actually with my voice.
Yeah. There, that should be better.
Thank you, Ben.
Yep.
Okay, up next we have Avishai Dekel talking about dark matter deficient cores.
I need Reinhard Genzel to come in. I want to address him. So.
Okay, we need Reinhardt. Farhan, can you get Reinhardt? Thank you. Okay, we have Reinhardt. Without further ado, Avishai Dekel.
Thank you. My talk is inspired by the last part of Reinhard Genzel's talk this morning. I'm trying to refer to it. Let me take this opportunity to congratulate Reinhard for the Nobel Prize that he got last year. And as he himself said, he's a loyal participant in this workshop, and maybe this has some part in his Nobel Prize. Maybe it will have part in his second Nobel Prize on high redshift galaxies. So I'm going to tell you about dark matter deficient cores in high redshift massive galaxies. And I'm going to tell you about a little bit about what Reinhard started to say. I'm going to tell you about the mechanism of compaction above a golden mass and how it drives a black hole growth about this golden mass. And I'm going to tell you about dark matter heating by dynamical friction and how together with AGN-driven outflows we can get the dearth of dark matter in those massive galaxies. So it's the old dark halo cusp core problem where simulations give us an NFW kind of cusp, but some observations give you cores. It's known for many years concerning dwarf galaxies, but the big surprise is that it's happening also in massive galaxies at high redshifts. You can model this change of slope, for example, by extending the NFW profile to a slope that varies. I like what Jonathan called the Dekel-Zhao profile, which is a slight different, but the great virtue of this is that with two parameters, it's not only giving you the best fit to simulated dark matter halos, it is also analytic. And you can really compute everything, including the energies, kinetic and potential, analytically. So this is what we have been using here in this study that I'm going to describe here. So this is the kind of observation that Reinhard did not have time to describe. What you see here is the rotation velocity by each component as a function of radius. And what you see on the right-hand side, you can derive the total velocity in this sense, and then you can look at the baryons, and you find that the difference gives you a dark matter component which dominates the inner part of the galaxy. We're talking about RE or few RE. On the other hand, on the left-hand side, if you get the total velocity after correcting for the dispersion velocity, the black is the observed rotation curve, and the baryons, the difference is very small, leaving very little room for dark matter. And this is the surprising type of galaxies which are baryon dominated within RE or 2RE. That's the kind of big surprise that started in this analysis, now reaching 100 galaxies. And from, again, this recent paper, Nestor et al., if you plot the dark matter fraction within RE as a function of the inner slope of the dark matter profile that you derive by analyzing the data, you get this group, which is a cusp with high dark matter fraction. That's what we expected, especially after adiabatic contraction into the galaxy. But you get also this surprising family, especially at high redshift, around redshift 2, which is the red dots here. Low dark matter fraction, below 20%, and tending towards a core in the middle. So the big surprise is that any simulations that I know failed to reproduce extended cores of 10 kpc in massive galaxies. And theoretically, based on my own work, I didn't expect supernova feedback to give you this in massive galaxies. It can do it in dwarf galaxies, but not in massive galaxies. So what on earth is the reason for this observational evidence for dark matter deficient cores? And why is it that it's happening preferentially above a threshold mass and at the redshift above 1, say, at 2? What makes this? And that's the kind of model I want to propose. Another way to see this, if you look at the distribution of the dark matter within RE as deduced from observations, and what you expect from an NFW Caspi halo of the same stellar mass. And if you focus on the red histogram, that's the high redshift, high mass end, and you see a strong deviation from unity for the whole sample, but in particular for the massive and high redshift galaxies, a strong deviation from any NFW kind of by a factor of 10 sometimes. So there's clearly a much flatter core associated with the low dark matter fraction. So I'm going to discuss two processes. One of them is the dark matter halo response to gas blowout. You take a Caspi halo, you blow out a lot of the gas, and you end up with a puffed up dark matter core. And that's very easy to understand from a very simple toy argument. Consider a system in initial virial equilibrium. Eject half the mass instantaneously while the velocity is unchanged, and you put half mass in here, and because of this square here, this becomes 0. You remove half the mass, you make the system unbound. That's a trivial argument for why this is kind of happening. Now, as I just said, supernova-driven outflows are ineffective in such massive galaxies, and AGN outflows are effective, probably, in massive halos. But if you simulate this, again, in any simulations that we know of, they do not produce extended flat cores the way they are indicated by the observations. So here's another mechanism which may help. And this is heating by dynamical friction. Constantly you bring in by mergers what we call satellites that build up the galaxy, and dynamical friction goes like the mass of satellites squared, and it's the mass at every point taking into account the stripping, tidal stripping. So the tidal stripping, this is the classical formula by King long time ago. What comes in is the density profile in the halo and the amount of rotation that you have in the inflow. And the point is that the more compact the satellite is, the bigger the mass that it retains as it spirals in, and the stronger the dynamical friction is. Now, this dynamical friction, of course, heats up the dark matter, and help it being puffed up. Again, in simulations, this is not good enough. It produces little cores, it heats up, but it does not give you the massive extended cores that you need. So maybe the two can work together, and that's the idea that I'm trying to convey here. A hybrid scenario, the idea is that dynamical friction on major satellite heats up the dark matter, brings the particles close to the escape velocity, ready to be pushed out in response to the blowout by AGN feedback. And of course, being hot by this preparation stage help you be more effective and hopefully get the dark halo cores that you wanted. Now, this immediately gives you the answer to the question, why at a given mass and a given redshift? Because, as I'll show you soon, satellites are compact above a threshold mass and at high redshift. That's where compaction is effective. And this allows the penetration and the heating. Also, the rapid black hole growth is expected post-compaction. Again, above the magic mass for compaction, and this will give you the strong AGN-driven outflows. So those two mechanisms really work perfectly if you're in the right redshift and mass range. So let me tell you a few words about wet compaction. First, the scale, the magic scale that we saw already today. Halo mass, where the efficiency of galaxy formation is maximal, which we blame on quenching in the low mass and the high mass end, and maybe on the black holes that appear above the golden mass. It connects to the time for efficient galaxy formation, and this comes mainly from the fact that the typical halos at around redshift 2 are of the golden mass. So if you blame the golden mass for the peak, you can also get an associated golden time for this peak. And that's because the pressure sector mass is roughly at the golden mass at those redshifts that we are talking about. And there are reasons for other reasons that point to the golden mass. There's the shock heating, above which we have a hot CGM, below this cold CGM, and there's supernova feedback, above which it's ineffective and below it's effective. They all kind of conspire to give you this magic golden mass. This is a compaction event in one of our simulations. You see here the compaction, a blue nugget forming in the middle as the gas goes in, and depletion, central depletion, and sometimes formation of a ring after that. So a cartoon way to look at it is that the gas mass within 1 kpc jumps by an order of magnitude, maybe because of a merger, maybe because of another mechanism that help you get rid of some angular momentum very quickly. And this is the compaction event. The star formation follows, star formation rate. The stars just grow up here, and the dark matter remains here, so you get a star-dominated central regions. That's the typical compaction event. To predict what observations will look like, you compute the specific star formation rate as a function of some measure of compactness, sigma within 1 kpc. You see this nice L-shape behavior, where from diffused you compactify to blue nugget, and then you quench to red nugget in this L-shape. And indeed, this is seen in observations, in this case from candles, where you can infer the same kind of behavior given the same L-shape observationally. In a study led by Mark using deep learning, we discovered that indeed there is a typical mass slightly below 10 to the 10th solar masses for stars where the compaction occurs. That's the compaction, the other ones are pre-compaction and post-compaction. So there is this magic mass for compaction that's going to serve us when we try to understand the creation of a core there. Before, on small scale, supernova feedback suppresses the compaction, and above it, the hot CDM, maybe AGN filtrate, suppress the compaction on large scales. And this leaves you the ideal mass for compaction and also for effective star formation, as we saw before. Now, the black hole growth is happening above this golden mass, and you can see this in this simulation from New Horizon. As a function of time, the mass within 1 kpc, you see this gas compaction event, and just following it, the black hole growth, which was suppressed before that by supernova feedback. And this is pretty typical for those galaxies. So the compaction drives the black hole growth above the golden mass, and that's, if I had the black hole mass, this is the cartoon version of how it grows at the same time of the compaction, namely at the same characteristic mass for compaction. Indeed, if you compare the simulations to observations, for Schreiber et al. Show us the incidence of AGNs in different types, having this sudden beginning of growth above 10 over 10 solar mass, and this is what we get for the black hole mass as a function of stellar mass, or if you want the bulge mass, the same L-shaped behavior, where the blue nugget in each of these galaxies is really where the turnaround is to the beginning of this rapid growth above the magic mass of 10 to the 10 solar mass. Now, how do you heat by dynamical friction? Let me show you a toy model very quickly. This is how you determine the tidal radius, and the mass within it survives. Again, it has to do with the mass profile and the circularity. I'm using the same Dekel profile, which allows me to change the slope and do it all analytically. And I can compute the penetration of satellite mass, what fraction of the initial satellite mass really gets into the cusp of the host galaxy. And this is going to be a function of all these quantities, and the satellite compactness parameterized by concentration and slope using the Dekel profile. So I compute this analytically, and then I ask, what's the work by dynamical friction? I use the Chandrasekhar formula, and I assume that the work is roughly the force times the size of the cusp, 10 kpc say, and this gives me the heating energy as a function of the initial kinetic energy of the cusps, as a function, the initial mass of the satellite, and the fraction that actually survives tidal stripping. And I can do the same thing for a cosmological sequence of satellites with a merger rate that I can compute analytically, assuming a typical 20% mass for the major satellites. And I get that energy, the relative energy added for heating in a tau times dV, tau being a Fourier unity, is a Fourier unity at redshift 2 for a fraction of 0.2 again. And this tells me that for cusp heating, you need a fraction of at least 20% of the mass of satellite to survive all the way to the end. So you need a compact massive satellites to ensure this happens. You better do it at higher redshift. And a tau for the unity, or a half, would be sufficient to get this for the unity. And that's the heating that you want, a heating for the unity compared to your initial energy. So you can quite analytically convince yourself that it's going to work. Now, about the compaction, here's a nice plot showing you the evolution of the density profile of a halo, of a satellite, in our case, not only the halo, the whole galaxy. You see pre-compaction profile, which is not very compact, and turning after the compaction, which happened between the blue and the red at some redshift around here, you get much more compact density profile, mass profile in this case. And if you fit a Dekel-Zhao profile, these are the parameters for the concentration and the slope. Concentration becomes higher, the slope becomes steeper. This is if you translate this to NFW, concentration and slope. And the whole idea is that since the compaction occurs from masses above 10 to the 11 solar mass, halo mass, if you have a host galaxy of 10 to the 12, it will have this kind of massive satellites which have compactified. And a toy model for dynamical friction, I put here the slope and the concentration. You see the mass penetration ratio. If you have compact satellites, post-compaction, you expect about 40% survival, above what you need, 0.2, and that's this. If you have a diffuse satellite, the example I showed you before, you end up with a much less mass penetration, not enough for heating up the cusp. And indeed, if you look at the energy, in a real time, the compact satellite gives you a factor of 2 to 4, either for a single satellite or for a cosmological sequence of satellites. And that's well above what you need for significant heating. The diffuse satellites, typical diffuse pre-compactions, do not give you enough energy for significant heat up. So you need this mass threshold to really get the heating right. And Fangju showed this already in his talk. If you look at the function of radius, the relative cusp heating, the compact satellites within 10 kpc is well above unity, but the diffuse satellite typically is less than unity, is not good enough. You must have the compaction for the heating to work. And the toy model really recovers very nicely the results from those semi-analytic simulations by Fangju. Now, the response of the dark matter to cusp and gas blowout, we started with something that Jonathan described already. We start in initial equilibrium, kinetic and potential energy, and density, steep density profile. We have a sudden gas removal. You change the potential energy without changing the kinetic energy because it's instantaneous. And then you have a relaxation process where the system adjusts again to a new equilibrium, both the kinetic and potential energy change. And this is the key, this was the hard part. And now we have a new method based on what Jojo Lee is going to describe, where we play a diffusion process in energy space and give each particle in a little time scale a little change in energy which equals the little change of the potential as the system relaxes. So just to illustrate this in one slide, we start with a potential well like this and a particle lying somewhere here with this kinetic energy. We remove the gas quickly, the potential change quickly, but we do it in small time steps. And applying this rule for each particle, you see that this gray arrow is reproduced by this actual new position of each particle. It turns out to be a very accurate process, and it allows you to compute the distribution function and the density profile, and this is a kind of test against an n-body simulation where we removed the inside. And note that this is R times rho. So this is a core, is something with a slope unity. This is the initial thing we start in a simulation, and in the model, this is if you put in mass, it's the contraction process, the inflow, and the dashed line is the model, the solid line is the simulation. It works very well, and it works very well also for a total removal of the gas, in which you make a very extended, nice core, extending to more than 10% of the via radius, which can be 10 or 15 kpc. And this simple model really reproduces the simulations very, very accurately. You end up with a core. So that's what happens. If you have a cold initial NFW halo, you just make a little difference when you get a strong outflow. But if it's a preheated NFW halo, you get a much, much stronger and a nice flat core by this mechanism. So a heated cusp is more responsive to outflow as we expected, and the trick may work by putting those two mechanisms together. It turns out that this core cusp is maintained hot by a cosmological sequence of mergers, and we get the outflow-driven core. I won't go into details. The challenge, of course, is to get stars to remain bound while the dark matter is pushed out. And for this, you need to start with some segregation. You have to start with the stars in a smaller radius than the gas and a smaller radius of the dark matter, which you may expect from the formation mechanism in which the stars from gas that have the most dissipation to get in. Also because this kind of configuration by Jean's equation gives you already a dark matter that's hotter than the stellar system. So you can end up with hot extended dark matter, which is more responsive, and that's what you expect. This is work in progress, and Jojo Lee is working on this, and we are going to apply the same model, extend it, and compare to simulations with a two-component system to overcome this difficulty and get a realistic system in which the stars remain bound. It's yet to be seen in cosmological simulations that resolve what we need to resolve. So what we need to do is simulations in which the resolution allows the two mechanisms to really be resolved. On one hand, you want massive satellites to be well resolved, and some work by Frank van den Bosch and colleagues tell us that you need many particles to avoid artificial disruption. So these simulations don't exist yet. And you need to boost the AGN feedback, maybe with clumpy accretion, the way Colin and I and others proposed we can do. Also, you want the ISM CGM to respond by clumps, which can make it more effective. And those two challenges are going to be met in future simulations, hopefully recover what we get from our analytic models. Now, maybe I'll skip this. Time is short. You can think of using similar arguments to understand death of dark matter in diffuse galaxies using supernova feedback. You have to worry about what replaces the compaction, which is a high redshift, high mass phenomenon. So my conclusions are, there is a golden mass, we all know, at roughly this mass and this redshift. You can expand this by supernova feedback on the low mass end, and CGM heating, maybe AGN feedback on the high mass end. Wet compaction happens in many, many galaxies. We have evidence for this from simulations and from observations. It happens near the golden mass, and it's responsible for many transitions in most galaxy properties. black hole growth, which is suppressed by supernova feedback on small mine in early times and allowed when the CGM becomes hot below and above the golden mass, is triggered by the compaction. That's the big drive that in this mass range allowed the black hole to start growing. And this is the key for what we need. So the dark matter deficient cores can occur in massive galaxies and at high redshift because dynamical friction heating is with the post-compaction satellites, which are compact above in this mass and redshift range. And the dark matter response needs the AGN outflows, which are strong once you cross this mass threshold at high redshift. And you may end up with the differential response you need. So that's the key to what I was talking about, yet to be reproduced in simulations that resolve both the compact satellites and the clumpy AGN. And maybe this can be borrowed to explain the low mass, low redshift dwarf dark matter deficient cores. Thank you.
Okay, could the next speaker go ahead and be setting up? We have time for one quick question.
Yes, Avishai, it seems to me that for your AGN-driven case, you need